Hello, and welcome to part 4 of our Guy Tries to Make Wall series, where I'm gonna try and make a wall. And this time it's gonna be bubbles. It's gonna be a bunch of bubbles. So I'm thinking of stacking some circles and then controlling the radius with an image. Not an image, maybe something else. And then making a CNC milled wall from it. And as per usual, I will show you the end result, the actual milled panel. That's the goal of these. So I guess, without any further ado, we begin. So the first thing that I'm gonna, do we do this in Rhino or Grasshopper? Well, do we start in Rhino or Grasshopper? I think we start in Rhino. So, in Grasshopper. So I'm just gonna create a rectangle. Yeah, let's do a rectangle. And let's make this, bifocals, god damn it. You don't need to repeat the bifocals part, this is just to show the names. So we create a rectangle and we say 3000 millimeters in X direction and 2000 millimeters in Y direction. There we go, perfect. And that rectangle, let us create a bunch of points inside of it. I think. So this is our rectangle. I kind of want to populate it with a bunch of points. So populate randomly. Populate 2D. Connect that like this. So that's our region and number of points. Let's start with something like 500. I think 500 is reasonable. It's actually not that many. Let's do 1,000. 1,000 points, like that. So these points, I kind of want to draw like a circle stacking, not stacking, packing, circle packing thing where there's a circle around each point and all of them kind of pack into this nice little field, so it's basically like a bunch of bubbles. I can show you what I'm after. It's much easier. Bubble foam image, kind of like that, right? Kind of like that. Not really like that, but maybe there's a little bit of variety going on here. I want it to be a little bit more gradient-y, but like the gist of it is this. So I want to do that, and I want to CNC mill that. Let's do it. Let's just do it. All right. So populate 2D, we have a bunch of bases for our bubbles, and we will be using, how is it called? Like in Kangaroo has like a goals, collision, image circles. There we go. We'll be using image circles command, which asks us for a bunch of points, and also it asks us for a mesh for us to drive the radius of the bubbles. So the mesh, basically it just takes the bright and dark colors of the mesh, and where the mesh is bright in color, the bubbles or the circles are going to be smaller and larger, and where the mesh is dark in color, the circles are going to be smaller. That's the idea. So how the hell do we create a mesh that has a gradient? Well, we have a rectangle, so from it we can kind of create a mesh surface, and the rectangle goes into the S input here. And let's just go to display, preview mesh edges, turn that on to see the divisions. And for U and V count, let's do something like 100. So 100 by 100 polygons, so 10,000 polygons, right? And basically I can just take this mesh, I can deconstruct it, Come on, mesh. I can deconstruct the mesh like that, and I get its vertex, face, and color information. And then I can construct it, right? But this time, as I'm constructing the mesh, I'll be using the vertex information, I'll be using the face information, but the color information, no. That one I create. And how the hell do we, well, actually, let's start hiding things because it's in the way. How the hell do we create color information? Well, we're going to be using RGB colors for that. Color RGB, and we use float, by the way. So in brackets, it needs to say F. I'm not gonna, it's gonna be faster. Just, that's all you need to know. This is much, much faster than the alternative. So color RGB F. And then for R, G, and B, if you use the same number, it's gonna go into grayscale. That's, you know, because gray is like 1 to 5, mid gray is 1 to 3, 1 to 3, 1 to 3 for all of these. Actually, I can show you. That's mid gray. Wait a minute. No, it's not. 0.5 is gonna be mid-gray because it doesn't go up to 255. Yeah, so now I can kind of control the brightness of it. A little bit boring, so we're not gonna be using that. Instead, I'm gonna show you a very, very cool little trick. And that trick is in Parakeet plugin, I think. Parakeet, Utilities, Mouse. We will be using mouse, and the way it works is if I just create a toggle, Boolean toggle, connect that to T, run it. See how there's a point that follows my mouse? Hell yeah, it knows where I'm holding the mouse. So that means we can have an interactive attractor point. Yep, that should be pretty cool. And we don't even, sorry, it's not just that, but also we can kind of create like we can record. We can use data recorder to record the position of the mouse. So if I just did this, wait, give me a second. Maybe like that. Then it's a little bit janky, right? I can kind of draw, but it's very janky. So we're not gonna use that. I'm gonna turn this to false for now and click the X to clear the what was recorded. Instead, I'm gonna use gate. Is it gate or filter? I never remember. It's gonna be filter. Filter, stream filter. And I'm gonna say when left mouse button is clicked, then you should parse the mouse position through the input 1. So you can kind of let me disconnect here and just run this so that you can see what the hell is going on. Every time now I press the mouse button, look at here, S0. That means right now the filter is pushing through whatever 0 gets, which is nothing, right? So it's pushing through nothingness. But if I press the mouse button, and I can kind of show it to you this way, wait. And puck. Now I'm holding it pressed. You can see that it's changing to S1, right? So now since the L output, which is left mouse button, is true, the filter is letting through information that is set to be in that's going into its one input named 1, so S1. So that's the idea, right? Every time I press the button, it just changes from S0 to S1. Now if I connect this to data recorder, and I kind of start clicking here, I can click wherever I want my attractor points to be. If I don't like this, I just press the X button here to delete them, and then I go again, right? Poke, poke, poke. So that's nice. Let's turn this off for now. Or actually, let's not. Let's add like 1, 2. Oops, that's my mistake. Sorry. Again, 1, 2. 2 attractor points, and then we turn off the false. The toggle, the mouse tracking toggle. And now our data recorder, it has, for some reason, 10 values. Don't ask me why it has 10 values, but probably a bunch of values on top of here. Doesn't matter. As long as all of them are located here, it's gonna it's gonna work. I forgot that you get the false statement. When I need to click on the false statement, it also registers here. Whatever. It's not perfect, but you get the idea. So now we get attractor points that we can just directly click on here with the mouse. With this, we can say, we can work with them like attractor points. So I'm just gonna say pull point. Points that are being pulled are our deconstruct mesh vertices, and data recorded are the attractors to which the points are being pulled. So we get the distances, and those distances can be remapped into values between 0 and 1 because that's what RGB color wants. So distances are being remapped according to certain bounds. So whatever the largest and the smallest point is, that's our source domain. Largest and smallest distances, not point, sorry. And if I connect it this way, now I can see, let's display, preview mesh edges, turn that off. Now you can see that the closer we are to our attractor points, the darker the mesh gets, right? Let's clear the data recorder and let's run the mouse registration, and let's just play around with this for a bit. 1 point, okay, 2, okay, 3, 4. Do you see what we're doing here? We are basically creating a Voronoi point cloud. So this is us creating a Voronoi sequence. Let's clear it. Let me just 1, 2, 3, 4, 5, whatever. And let's just turn it off for now. So I am initially, this is how Voronoi works, and we've done that interactively. Okay, so we have a mesh that has colors now. And remember image in circles? Yeah, that's where the mesh goes in. Bam, just like that, as our driving force. Then all we need to do is specify what's the minimum and maximum radius of the circles. So wherever it's white, these points, the circle here, how big should that be? And wherever it's black, how big those circles there should be. So the one that's white, the one that's black, the smaller circle radius, I'm thinking like 1.5 centimeters. And the one that's large, so 15 millimeters, let's not go beyond 50. I feel like 50 is, yeah, 50 is pretty big, so 10 centimeter diameter, right? And for the curves here, optional collision curves, I want the outer perimeter to be like a colliding, like a perimeter which doesn't let the circles fall out. So our rectangle is going to be our additional colliding curve input here. All right, so that's our goal. And as usual, with any goal, we will be using a solver, a kangaroo solver, which we will toggle reset, or sorry, toggle turn on or off, which we will use a button to reset, and we will get a bunch of vertices out here and the output as tree. This is basically just like circle size. We're gonna get that out as well. So we can just create a circle from those. Circle around the vertices with the radius dictated here. Let's clean this up a bit. Hide all of that. And you can see that the circles are intersecting. That is normal. If I reset and I run this, then it automatically reshuffles the circles so that they don't intersect. And now I can see that there is not enough circles, right? So the density is too, like I could start increasing the radius here and they would reshuffle, but then the difference in size of them, you know, wouldn't be that great. So instead I'm gonna just say, let's keep it 15 and 50, but instead I'm just gonna say we need more circles. So instead of 1,000, let's do 2,000. Like that. And you can see some of the circles got pushed away. Let's see if we reset, if it's gonna, yeah, if we reset, they get contained. And now everything seems to actually work out, except here. We could push them a little bit more. So instead of 15, let's do like 16. Yeah, 16 seems to be better. Yeah, we get ourselves a little bit of a pattern. Let's hide the mesh so that you don't see the gradient, but this is how it looks like. Looks nice. All right, what's next? Next up, we need to... I'm stopping the simulation, by the way. Next up, we need to somehow create a three-dimensional form from this. So the question is, how do we... I'm, by the way, just checking if my camera still works. It seems like it does. So let's first of all build a data dam. A data dam that doesn't let information through until you let it. And I think for the data dam, we will need these two outputs as well as the rectangle out, just the rectangle. So I'm just gonna say ABC. There we go. Rectangle goes into A, vertices go into B, and O output goes into C. Just like that, a big ass data dam. I can even group this and make it like color. What? Oh yeah, alpha green, like that. Just so that it's easy to remember that, oh, I do need to press the play button to let the information through. Let's create a bunch of spheres. Mesh spheres, not regular spheres, mesh spheres around these points. So now all of these are not circles, but actual three-dimensional spheres. Let's change this to shaded view. Looks kind of nice. We don't need that much of a resolution, so let's just use like 12 for U and V values. Like that. So we have a bunch of spheres. That's good. What else? What else? What else? I kind of want to... Well, actually, instead of a rectangle, let's just parse through the mesh. This colored mesh. So datadam A input, instead of a rectangle, we use the constructed colored mesh. Press play. Let's just use mesh join. The plate with the spheres, hide everything, gets joined. Oh yeah, and we need to flatten the input. Make sure that mesh join M input right click is flattened into one list. Now it all is one single mesh that we will need to rebuild into like a proper, like a surface. How do we do that? How the hell do we do that? Well, first of all, the edges are gonna be very tricky. I don't want it to go all around the edge perfectly. So let me just move all of this slightly down. Let's create another rectangle. Let's create another rectangle. Come on. And let's just say it's the same size, 3000. Oops. So the size is initially the same, 3000 by 2000. But there is like an offset. So can I just do an offset? I think I can, right? So this rectangle gets an offset. Offset curve with distance of, let's say, 1 centimeter. So minus or 10, and it needs to be negative. Negative 10. So it goes in by 10. And then it needs to, this curve, this rectangle needs to be moved up by some number. So it needs to hang above our messy mesh. So let's just do like something simple, like 1,000. 1,000 a meter above, like that. Then we take this and we divide it. Since this is like a region, it can be also read as a surface. So we can just say divide surface. We can divide it into U and V values, and let's use like 100 for now, just like a small value. Oh, sorry, not 100, but like 101. Come on. Don't ask me why 100, or actually ask me why 101 in the comments. That's how you get comment engagement. Anyway, we get our divide surface output here. Let's flatten it. Yeah. So right click the P output of divide surface and flatten. And let's just take all of those points and project them down onto this shape. Project point. So these are the points that are being projected. Direction is going to be Z, but actually it's going to be negative Z. Oops, because down, right? Down is negative Z, and geometry is going to be our mesh. So now all of these are projected onto the mesh, and it should work technically. Let's just do one little fix up to make sure that as the point is being projected onto a sphere, it's only the first hit. So imagine a sphere and the point is falling and it hits the sphere, right? So it's only this point that's registered and it doesn't keep falling through and creating a second point. So you only care about the top hit on the sphere. So when we use project point, let's right click the P input here and graft it so that every point is calculated separately. And then the P output here, let's just say list item. And basically list item just gives you the first item from the list. So every time when there's a sphere and there's like 2 points that are being generated, it only will take the first point, always. And that one gets flattened. No, I keep missing it. Flattened, there we go. And from there on out, we just construct a surface. Surface. Plane surface, no, surface from points. Surface from points, there we go. Point input is the list item output, and U count is from the vertex count, or from the UV count here, like that. It's gonna complain, don't worry. The reason why it's complaining is because if you're familiar with the channel, we always do this. Divide surface. If you have a surface and you divide it with sliders saying 2 by 2, it's actually going to generate 1, 2, 3 by 1, 2, 3 points. It's going to have like 2 surfaces by 2 surfaces, but the amount of points is going to be 1 extra because there's a start point and an end point. So for the U input here, I need to right click on it, go to expression and choose to use x plus 1. So any amount that comes in is going to have 1 extra. And then it does indeed generate a surface for us. Now I can hide everything except the final surface and take a look at it, and it looks like garbage. Don't worry, we will fix it. Just to let you know, the files here that you see are available for Patreon supporters. So if you're a Patreon supporter, you get these files and every single thing that I've done on the channel for free. Well, not technically free because you're a Patreon supporter, so you're supporting the channel, but you get what I mean. But you know, if you don't wanna, or if you can't support the channel through money, then you can just straight up follow along with the tutorials and, you know, reach the same end goal. So this is mostly for the lazy people out there. Link in the video description, as per usual. Okay, back to the program. The reason why it looks like garbage is because we have 101 vertices here, right? Or divisions. So it's not enough resolution. If we have 200, it's better, isn't it? It's much better. If we have 400, let's double that. 400, it takes much longer, but it's even sharper. So let's do something like 500. And 500 should be, you know, pretty close to good enough, to where the CNC mill inaccuracies in the CNC and the material will be the culprit of something that's messy, right? So this is us getting our neat and dandy surface. Let's bake it into Rhino. And actually let me save this. So I'm just gonna I'm gonna get this ready for wall 4. Yeah, sure, we can save it here. Wall 4 for the Patreons. And this is wall 4. Okay, and now to finish this up, first of all, let's take a gander at it with Arctic view. Yep, looks like a bunch of balls, doesn't it? A bunch of balls. Oh, by the way, one more thing. If you want to have these bubbles overlap a little bit more, you can always take the radius values and just multiply them by, let's say, 1.2. Or is 1.2? Yeah, let's do 1.2 and connect them that way. So this will force the spheres to overlap, and in turn, it's taking forever, and in turn it's gonna force the surface to, I'm just trying my best here, insert, I'm just gonna show you like a comparison between the two. It's gonna force the surface to be a little bit more smoother, I guess. Let's see if there's any visible comparison between the two. Oh yeah, there definitely is. You know, the gaps here are much more prominent than they are here. So keep that in mind. Another thing to note is that I actually like the one with less gaps. So another thing to take note of is the thickness, the height of this particular pattern. We are gonna be manufacturing this out of 18mm MDF. So I do need to create a bounding box for it and scale in 1D the form together with the bounding box to something like 16 millimeters, so that it's not too obnoxious in terms of the not obnoxious. How do I say this? So that it doesn't force us to glue a bunch of MDF boards on top of each other and then deal with the seams, which is in turn very obnoxious and very annoying to deal with. We want to mill this out of one MDF board, one thickness of an MDF board. All right, so we have that. Now, we do need to actually, let's go for Arctic view. Create a, like find a place or find a pattern where we're going to be which we're going to be extracting. So I'm just going to create a rectangle that is 500 by 500. This rectangle right here, and I'm going to find a pattern somewhere here. I think this might look pretty nice. Right in the middle. And this is going to be the pattern that we're going to be CNC milling. So of course I'm not going to be milling out the whole damn wall. That would be a waste of material. Instead, the tests are going to be 0.5 meter by 0.5 meter. That is more than enough to get the idea of how does the CNC deal with the form here. And how does the final aesthetic look like. So there's going to be a little bit of a gradient here. And at this point, you probably already know how we do this. We create a bounding box. We scale 1D from here to here, 18 mil. That's literally our stock. You know how big our MDF board is. I just mark it with a point. I get the outer perimeter with DUP border, DUP border. I scale this to 0 to flatten it out. Move it from its corner point to that point that I just created that marks the bottom of our stock. And I just loft between the two. Delete, join, cap. Did I cap? Cap. One closed object, right? I can type in what, and it says valid polysurface gray. That means, usually it means that we get, if we mesh this, we create a valid mesh from this. And, you know, this is the bubble form that we get. If I were to look at this with my, let's say Evangelion red, this is not red anymore, but it is what it is. This is how it looks like. Actually, we should probably take a look at the full wall, because that might look even nicer. Why is this not red though? Oh yeah, I changed this in my previous video to blue. Don't worry about it. But hey, that's a lot of bubbles, isn't it? A lot of bubbles with varying radii. And here the radii don't follow the pattern that well. We can actually control this a little bit more, should we? Like we are done here with the script, so I guess we can mess around for like a minute or so to try and get a better result with this. So let's take a gander at our circles here. Because the circles, the pattern of the circles does look like it worked. It's just the surface, or actually perhaps the surface also worked. It's maybe just me who's expecting more. Also, why the hell is there like a gap there? That's weird. So maybe we don't play around with this. Actually, I do want to. I do want to. So we just reset this. Oh yeah, and we do need to stop this. And let's not look at the bubbles for a bit. Instead, let's clear the data recorder. And let's just add more. Let's do corners. 1, 2, 3. Come on. 3, 4. Let's do here like that. And actually, I think that's fine. Not more. So then we stop. Come on, stop. We reset the simulation. I said we reset the simulation. It doesn't look like it's resetting, but maybe it is. Oh, it immediately crashes. Never mind. It doesn't. So now it's gonna relax a bit. There's a few circles that ran away. That's not a big deal. That's fine. Stop it. Press play. Then now this is heavy, so we need to wait at least like 10 seconds or so. Real quick. I think it's done. Yep, it is done. Surface from points. We take a look at that. Insert to bake it out. Not Arctic. I do enjoy the Evangelion red. And again, one circle that's just doesn't fit. That is just missing. But yeah, we get our little little beads with the high density areas here and there, and lower, or not lower density, but large beads right here. And there was some sort of a mishap happening here, which is fine. Yeah, so that's how it works. Let's CNC mill this bad boy out and take a look at what we get. So for you, it's gonna be a second. There it is. There it is. So it's, I think the resolution of the bubbles or the dots, I think that's a little bit too big for this type of a panel. So it would work better if I had either a bigger panel or a larger amount of points. Because here it's a little bit too uniform, I would say. I should say. But still, you get the idea, you get the point. And imagine this being like a pretty large wall. That might look pretty cool. But if I were to do this again, I would definitely amp up the resolution. By amping up the resolution, I mean, come on, airplane. By amping up the resolution, I mean amount of points, right? Just to get a little bit more of variance here. But all in all, I'm pretty happy with this. So, hope you've enjoyed this one. Leave a like, subscribe, and I will see you in the next one. Later.